Hello everyone, welcome to this video tutorial on a finite element analysis, a practical approach using Ansys. So myself Shankar, Assistant Professor of Mechanical from Tyagarajar College of Engineering, Madurai. Okay, so before starting with any FEA problem, so I'd always suggest to see the steps involved in FEA analysis using any FEA softwares. Basically there are three steps: pre-processing, processing and post-processing, and these are the steps within pre-processing which the user has to do, processing which is nothing but solving the equation which the computer does for you, and finally user has to see the results. So in today's video tutorial, so far we have completed all the thermal category problems. So we'll shift on to the next category, which is thermal. So far we have seen the structural analysis problems. So now we'll move on to the thermal problems, right? So we are going to see three problems in thermal analysis. So one is the first one in this video tutorial. We'll be seeing about simulate and verify the temperature and heat distribution, effectiveness and efficiency in a fin using 3D elements. So this is the first exercise, this is the today's tutorial, and then we'll go on to composite wall, cylinder and sphere using 2D, and finally a composite wall using 1D elements. So in structural you can see that we moved on from 1D to 2D, and finally we ended up with 3D, and here we'll just do it the opposite way. So first we'll see the 3D modeling, 3D analysis, then we'll see the 2D and 1D. So except the difference is that in structural, the 3D modeling and analysis we done it in Ansys Workbench, whereas here in thermal we are going to do this 3D analysis or the 3D modeling and analysis of this fin in Ansys APDL itself. So that's the thing. Okay, let's get on. So before getting into the problem and seeing how we are going to do that, let's see a short introduction on this fin. So what is a fin? Okay, so fin, what is the need for a fin basically? So there are numerous situations where heat is to be transferred between a fluid and a surface. In such cases, heat flow depends on three factors mainly. One is the area of surface, temperature difference, and convective heat transfer coefficient. Basically we cannot very much vary the temperature, and varying the heat transfer coefficient requires more energy. Varying these two requires a lot of input energy, whereas this is one thing where you can increase the surface area without much input energy, right? So this is where this fin comes into play. So just let us see a small video on this fin.
Here we will get introduced to fins. Have you ever noticed the extruded portion of the surface of AC, IC engine, transformer, electronic circuit, etc.? Do you know what these extruded portions are called? Yes, they are called as fins. Now the question arises, why are these fins used? Let us try to answer this question. The primary objective of using a fin is to increase the rate of heat transfer. To understand it more clearly, let us take an example of an IC engine of a bike. We see that due to continuous working of engine, large amount of heat gets generated. This increases the temperature of the combustion chamber of the engine to a very high extent. Such increase in temperature may lead to severe ignition problems. To prevent such problems, the heat should be dissipated as early as possible. Now to increase the rate of heat dissipation, we need to increase the surface area of the engine. But we know that there is a limited space in the bike, so we cannot increase the area by enlarging the engine. But we can solve the problem by introducing fins. We see that because of fins, the surface area of an engine increases and a large portion of engine gets exposed to the air. This helps an engine to lose heat at a faster rate.
Here we observe that heat gets transferred from engine casing to fins through conduction, and from fins to air through convection. This was the brief introduction to fins.
Right. So I think you would have understood what is a fin from this video very clearly, right? So fins are nothing but extended surfaces which are used to increase the surface area without increasing the size of the particular object or a particular machine component, right? So fins are thus used whenever the available surface area is found insufficient to transfer the required quantity of heat with the available temperature and heat transfer coefficient. So in case of fins, the direction of heat transfer by convection is perpendicular to the direction of conduction heat flow. So there are cases which this don't apply, but most of the cases this can be true. The conduction in fins is considered to be one-dimensional, though it is essentially two-dimensional, and this is acceptable as long as the length along the fin is much longer to the transverse length. So these are some of the things you would have studied in your theoretical part, right? I'm not going to get into this later, but the process of heat transfer with the fins is often termed as combined conduction and convection system. So we are going to have both conduction and convection in fins, right? Basically these are the different kinds of fin profiles. So rectangular and circular annular and longitudinal, triangular, trapezoidal, circular, semicircular, annular, cylindrical, like tapered, and like parabolic. So these are the different kinds of fin shapes, profiles that are available, right? And so this is the general derivation for a fin. So I'm not going to get into it. So I can see this later on. I'll give you the attached document for this fin. So here it is. So this is a document for if you're interested to really read about the theoretical content. I'll attach this document. You can read about it all the derivations and all the formulas from this document clearly, right? Now I'll just keep on, and so this is the formula for temperature distribution in a fin. Basically in a fin there are four boundary conditions, four types of boundary conditions which can be applied to a fin. So first is a long fin, second fin a short fin end insulated, the third fin short fin with end convection or the convection at the tip, and fixed end temperature. These are the four things, and in a moment I'll get into all these four and I'll explain what these four boundary conditions are, right? So as far as now, the formula for finding the temperature distribution in a fin for the both four boundary conditions are given here, and the formula for heat transfer rate or heat flux or heat distribution, the formula are correspondingly given here, and this is the formula for fin effectiveness, and this is the formula for fin efficiency. Just go through this. It will be available in this slide. I'll give it to you, and this will be helpful while doing the theoretical calculations to compare with Ansys, right? So now I hope you would have understood what is a fin, right? Now let me get into the problem which I am going to solve, right? So this is a problem which I'll be solving, right? So this is a fin of a constant rectangular shape, constant square shape of side 12 mm and total length is 160 mm, right? And one end of the fin is it is at a temperature of 200 degrees Celsius, right? And the surrounding atmospheric temperature is 35 degrees Celsius with a convective heat transfer coefficient of 22 watt per meter squared Kelvin. The fin is made up of such a material that it has a thermal conductivity of 51.9 watt per meter Kelvin. So this is my given problem, and so what I have to find the temperature distribution. So what would be the temperature at this end? So when it is 200, so convection is going to happen all over the surface, and then there is going to be a minimum temperature at this end. So that is the temperature distribution along the length, and also this minimum temperature which I am going to compare theoretically. And the heat flux, so what is the heat dissipation rate or the heat transfer rate to the environment, and in watt per meter squared or mm squared. So that I'm going to find, and I'm going to find the fin effectiveness, I'm going to find the fin efficiency, right? And temperature at a distance of 40 mm from the base. So basically I can find from this theoretical paragraph here the fin effectiveness. So fins are used to increase the heat transfer area by increasing the effective surface area. So when fins are not present, the heat convected by the base area is given by this formula. So the ratio of these quantities, which is the ratio of heat transfer rate with fin divided by without fin, so that is going to be the basic fin effectiveness formula. And the fin efficiency, you can find it here. Yes, yeah. The fin efficiency can be defined as the ratio of heat transfer by the fin to the heat transfer that will take place if the whole surface area of the fin is at base temperature. So this is the ratio of fin efficiency. So I'm also going to find the fin efficiency, and I'm going to find the temperature at a distance of 40 mm from the base. So basically in Ansys I'm going to find out only the temperature distribution, heat flux, and the fifth one, which is temperature at a distance of 40 mm. But the fin effectiveness and efficiency I'm going to calculate with the data that I get from this heat flux. So this is again a theoretical part. We can't find the fin effectiveness and fin efficiency directly from Ansys, but instead for the Ansys results for calculating this fin effectiveness and fin efficiency, I'll use the heat flux that I have obtained from Ansys, right? So this is the whole problem definition. So so this is going to be my model problem. So a square prism, right, with one end at 200 degrees Celsius with corresponding cross section. So this is my problem, right? So the second step is going to be element selection. So as I already told you, I'm going to use a 3D element, and so as I basically in structural, you could have seen that we did the 3D exercise in Ansys Workbench. The reason I told you is that solving 3D problems in Ansys mechanical APDL is a little bit difficult, right? But there are some simple cases where you can solve the 3D problems in Ansys APDL itself. So fin is one such problem. It is a simple rectangle square prism problem, and even though if you draw it as a 3D element or a 3D model, you can solve it in Ansys APDL itself. You need not go for Ansys Workbench. But for complex analysis, like I'll just show you one example. So I have done this. So what I'm going to do is this is my bike. So out of interest, I have done this. This is a old project which I have done earlier. So this is my bike, Hero Passion X Pro. I wanted to find what is the heat transfer rate in my bike using this fins. In this engine, there are fins. I wanted to find basically out of interest. I tried this out, right? And so this is how I model my fins using the reference image as my bike. In SolidWorks, you can find I have modeled the engine outer body, and I also modeled the fins around that. And the heat transfer, the air, as the bike moves forward, the air is going to flow, and this wheel and this frame, these are the two things that are in the way which blocks the air supply to this engine. As you know, this Hero Passion X Pro, this bike is a air cooled engine, so you don't have separate cooling. So only as you move forward, the fast air that comes from the forward, it is going to cool the engine. So I have basically done a CFD analysis on this, and so this is the model after you remove the image. So this engine, the fins, the frame, and the wheel and the tire, right? So this is the 3D image that you can see, and here are the results. So you can see as the temperature, you can see the red color here, as the temperature is building up, here you can find a lot of heat being transferred. But as the fins are there, fins helps in effective heat transfer, which you can see from the blue color colors here, which shows a reduced temperature due to the presence of fin. So this is CFD cum thermal analysis. This is a little bit complex and little bit out of scope for our syllabus, and so this is a velocity plot. So I have taken that the bike is going to travel at 30.5594 meter per second or 110 kilometer per hour. So that's the maximum speed of my bike. So I have taken the maximum speed to analyze how my temperature distribution would be in my bike. But we are not going to do something like this. We are not going to take this complex analysis, get it into Ansys Workbench or any other software, and we are going to see these colorful plots. No, we are not going to do that. So this is one thing that is complex. If you want to do this same analysis in Ansys APDL, then it's not going to happen. You can't do this, right? It's very, very difficult, right? So if you want to do one analysis like this, if you want such analysis like this, then you have to go for Ansys Workbench. But as I'm not going to do this, I'm going to do only a simple 3D analysis, then I can do it in Ansys APDL itself. No worries in that, right? Okay. So for this, I'm going to use the 3D element, which is brick 80278, and it's a 3D thermal conductivity capable element. It has a temperature degree of freedom at all its nodes. Okay, so these are some theoretical part about it, right? This is the second element selection. The third is going to be the material property. So the material properties, my fin is made up of such a material which has a thermal conductivity of 51.9 watt per meter Kelvin or meter degree Celsius. It doesn't matter. You know that the formula for thermal conductivity or the Newton's law of convective cooling, you know that this temperature is only the difference in temperatures, and which means that if you substitute it in degree Celsius or Kelvin, it doesn't change this value. It's not going to be 51.9 into 10 to the power or something or plus 273.15. You don't need to add any factors, because this Kelvin or degree Celsius, whatever you put it, it is always 51.9 watt per meter Kelvin, and it is always 51.9 watt per meter degree Celsius, because it is just the change in temperature, right? So change in temperature is same in Kelvin and Celsius scale, right? Similarly for the convective heat transfer coefficient, right? And so this is the material property that I'm going to give, which is thermal conductivity. And students often get wrong that convective heat transfer coefficient is also a material property. No, it is not a material property. Of course, it depends upon the material, but there are also other parameters which the material, which this convective heat transfer coefficient depends on, right? So this is not a material property, so I am not going to give it as an input in this section, material property section. The only material property that I am going to give it is a thermal conductivity. And try to switch over to thermal analysis, because don't stick your mind with the structural analysis, and don't try to give Young's modulus and Poisson's ratio as such things, because we have shifted our focus on thermal analysis. In thermal analysis, you only need thermal conductivity, heat transfer coefficients, so these kind of constant values. You don't need Young's modulus or density or Poisson's ratio whatsoever, right? So leave that all behind and shift your mind to thermal analysis. And the second is section properties. As I'm going to model it as in 3D, no section properties are required for me. So modeling the problem, as far as modeling the problem, I'm just going to draw a square prism of cross section 12 mm cross 12 mm with a length of 160 mm, right? So next comes meshing. So mesh attributes, which I don't need here, and I'm directly going to divide it into segments, and I'm going to mesh my problem, right? And so as I already told you, there are 4 boundary conditions in fish. Sorry, this is not buckling, so I just forgot to edit. It's fin, right? 4 boundary conditions in fin, which are long fin, short fin with one end insulated, short fin with one end convection, short fin with both the ends at base temperature. Among these 4 boundary conditions, this long fin, which means the length is infinite. Basically, in real world, we can't have a fin with infinite length, so that's impossible. So this is only works out for an ideal theoretical analytical condition. It does not work out in real world. Hence, we are not going to solve this boundary condition in Ansys. We are going to take only these 3 boundary conditions, which is short fin with one end insulated, short fin with one end convection, that is not insulated, and short fin with both the ends at base fixed temperature. So I can also input a word called fixed. So short fin with both ends at base or fixed temperatures, right? Okay. So we'll see one by one. So first one, which is short fin with one end insulated. So again, I'll change this. Sorry for the trouble. Okay, right. Short fin with one end insulated. So this is my fin, right? So this green color, I'm going to give an input of 200 degrees Celsius, and this other end, I'm not going to give anything. I'm not going to give any convection at this. The convection is only going to be along this 4 rectangular faces. So this parallel 4 rectangular faces, you are going to have a convection atmospheric temperature of 30 degrees Celsius and convective heat transfer coefficient of 22 only along these 4 longer faces, not in this one short end. So this is short fin with one end is insulated, this end insulated, so no convection at this end, only the convection is going to happen at this all 4 faces. The second boundary condition, this is one thing. So I'll solve this, I'll get all these results. Once I get all these results, then I'm going to go again, change over my boundary condition to that, such that this end is not insulated. That means the convection is also going to take place through this short face, right? So this is the second boundary condition. Then once I give this boundary condition, I am going to solve my problem again completely. Then I am going to get my results. Once I got the results, then I am going to switch over to the next boundary condition, which means this both ends, they are at 200 degrees Celsius. So the temperature is going to conduct from here, and the temperature is going to conduct from here, and somewhere along the midpoint the temperature is going to meet, and that is where you will have the minimum temperatures. Whereas in this case and this case, the minimum temperature will be at this orange color end, whereas for this fixed short end with short fin with both the ends at base temperature, the minimum temperature is going to be somewhere around the middle, right? It depends, right? Okay, it's here, you know, the base temperature are same, hence you can clearly say that the minimum temperature is going to be exactly at the middle point. So this is all about what I'm going to solve. So I'm going to basically solve 3 problems with 3 different boundary conditions, right? So let's see how to solve in Ansys. Before getting into Ansys, let me show you the theoretical results. So this is a fin, which is a combined convection system, which I already told you. So I'm going to find all these things both in theoretical and Ansys, which I have already done here. So I'll directly show you the results. The calculation part, you can work it out and you'll always get the same results. So as I already told you, the first is long fin, where x is infinite, which is impossible in reality. Hence, which is not, I'm not going to compare it with the Ansys. These red color values, these are only the theoretical values, and there are no Ansys values for this case, because I can't solve it in Ansys with infinite length. It is impossible. So I'm just going to leave this out. So the other three conditions, short fin end insulated, short fin with end convection, and fixed end temperatures, base temperature, both the ends will have base temperatures, right? So the black color value are my theoretical value and the green color value are my Ansys value, which I have already done and I have already given as input. But anyhow, I'll just show you, I'll just solve in Ansys and I'll once again verify all these values. Here you can find that temperature distribution and heat flux, these two values, these two data I'll directly get in Ansys, and similarly these three data, the first three data I can get directly from Ansys, but this fin effectiveness and fin efficiency I'll not directly get from Ansys. Instead, to get this green color value, what I'll do is that I'll use the corresponding Ansys heat flux, I'll divide it with the HA into TB minus T infinitive, and I'll get this value. Similarly, for fin efficiency, I'll use this value to get this value, and I'll use this value to get this value. So this is what an overall overview on my theoretical and Ansys calculation. Now let's get into the Ansys part to see how we can solve this problem. Right. So get into the start menu, open Ansys 19. So I have my 19 version, and get to mechanical APDL. Yeah, here it is, mechanical APDL 19.0. Just open it up. Okay, it's just opening up. Just wait for a moment. Okay, I'll just close this data which is unnecessary for me now. Right. Yeah, it's opening up. Oh, my system is a little bit slow, so please bear with me. Right. Here we have, right. So get to the preferences, and instead of structural we are going to solve thermal. So don't tick on structural as usual, right? We have now moved on to thermal analysis. So click on thermal and click on OK. Now get to preprocessor, element type, add. So as this is a 3D element, get to solid, and you can see all the old elements, which is bar element, beam element, have all gone because they are structural elements. We have all new elements here. I will discuss one by one in the later session. Now as far as now, I'll select this solid and I'll just come over down here, and here it is brick 8 node 278. So this is the element that I'm going to use. I'll click on OK, then I'll click on close. Next comes the material properties. Go to material properties and thermal, conductivity, isotropic. So the conductivity value here in my case, it's going to be 51.9 if I'm not wrong. So this is the first problem that I'm going to solve. Short fin with one end insulated. So this is the first thing I'll solve. So my conductivity value is 51.9 watt per meter Kelvin. So as the length units are in mm, I have to change this conductivity value to watt per mm Kelvin or watt per mm degree Celsius, which doesn't have any effect, right? So 51.9, it's watt per meter Kelvin. So I have to change it to mm, which is going to be into 10 to the power minus 3 watt per mm Kelvin. So as you can see here, the meter is in the denominator. If I have to change this to mm, it's going to be divided by 1000. When it comes into the numerator, it's going to be 10 to the power minus 3, right? So that's what I've given here input. Okay. So once you see here, you can always, or you can find convection or film coefficient. Don't give this input here, right? So this is not a material property, so I can't give this convection as an input here. So don't give the convection as a material property here. Just forget about it. Just only give the thermal conductivity property here and close this database. Now come to, I don't need any sections because I'm going to directly model it as 3D. So model, create. So there are two ways you can do it. One, you can keep the key point, then you can join them using lines, then you can create areas, then you can use the operate command, extrude command to extrude that area. But this is a lengthy process. I'll directly create the volume. I'll go to block by 2 corners and Z. I'll select this, and my starting corner is 0, 0 origin, and my width is 12 mm, and my height is 12 mm, and my depth is 160 mm. So okay. You can see a square is created. That's because we are viewing it in the front view. If I change it into isometric view, you can see the square prism fin is being created, right? Okay. Now that the modeling is completed, just with a simple step, I can complete this modeling. That's all. But if you have to do it using these key points and line method, it's going to be taking some while. I'm not going to get into that. I'll directly go to meshing. So mesh attributes here I don't require because it's made up of single cross section. It's made up of a single material. So I don't need to go for mesh attributes. I'll directly go to size control, manual size, lines. Instead of all lines, I'm going to choose picked lines, and I'm going to select all these 4 lines, the 4 lines. So you can see the 4 lines being selected. These 4 are nothing but this length, the bigger lines, the longer lines, which is along the 160 mm lines. So these are the 4 lines that I have seen selected. You can't find that these 4 lines are, whether you have some doubt whether these 4 lines are selected or not. You can verify it here. So the count is 4, which means I have selected the 4 correspondingly correct, right? Click on OK, and I'm going to divide them as 160 element. So as the length is 160, I am dividing it with 160. But it is not necessary like you have to do it similar. You can divide it into 500 elements, or you can divide it into 1000 or 10,000, depends upon your computer juice and memory that you have. But as far as now, I'll just divide it into 160 element, and OK. Then I'll choose pick the lines. I'm going to select the shorter lines here, 1, 2, 3, 4, and this shorter lines along this square here, right? So totally I have selected 8 shorter lines. I'll click on OK. Now I'm going to divide all this into 12. And again, as I told you, this is not necessarily that you have to select the number of divisions as same as the length of this line. No, it's just something that I like to do, which means that if you do this, then each element is going to be of 1 mm length. So that's the overall point here. But it doesn't matter that you have to do it's same as what I'm doing. You can try your own approach. So once the size control is completed, you have to go for mesh, volumes, and select free, and OK. Click on OK. Right, so it's going to take a while to mesh. So you can see the element count. So it's around 27,300 elements are there. Okay, so just zoom it out to show you what has actually happened. So a triangular element, so it's not basically triangular, it's quadrilateral. So on outside you can see triangular, but as you go in, it's going to be quadrilateral. In this triangle, the length of this each line in the triangle, each side of a triangle is going to be 1 mm, because I have divided the length into 160, which is the length of my fin, and I have divided the this shorter lines as 12, which is the length of the square, right? So the each element, it is going to be of a triangle with side as 1 mm. But it's not necessarily that you have to do like this, but make sure your fin is the number of elements is as fine as possible, your meshing is as fine as possible. Only then you'll get your result closer to the actual analytical results, right? Okay, once the meshing is done, I'll go for boundary conditions, loads, and here the boundary conditions are going to be, here the boundary conditions are going to be right. So this base temperature, and I have to apply this convection, and as this problem is end insulated, I am not going to apply any convection. These are the two things that I have to do. One thing, that I have to apply base temperature of 200 at this face, and along all these vertical faces, longer faces, I have to apply this convection value and the atmospheric temperature. I have to do these two things. Okay, let me get it to Ansys once again, right? So define loads. So here, as we are solving a thermal problem, I am not going to fix any sides. I am not going to apply a pressure or a force, because it's only in structural that you have to fix a given structure. Here the fixing is not required. Here the boundary conditions are only going to be in the form of temperature, and it's going to be in the form of convection or radiation or something like that. So it's not going to that, it's not necessary that you have to fix this line or you have to fix this edge. No, it's not like that, because the problem is a thermal problem. So keep that in mind always. So thermal temperature on area. So I'm going to apply a 200 degrees Celsius in this smaller face. This base temperature is going to be 200. So I'll select this temperature and I'll give on 200 degrees Celsius, right? So keep that in mind, whether you are giving it as degrees Celsius or Kelvin, because whatever you give here, it's going to be the unit of the result. If you give it here in degrees Celsius, then the answer is going to be in degrees Celsius. If you give it here in Kelvin, then the answer is going to be in Kelvin. So make sure you give it in correct unit. So it's going to be 200 degrees Celsius. I'll click on OK, and next I have to apply the convection, which means which is right here. Convection I'm going to apply in this all this longer phases, right? Convection on I'll change this to volumes, which would be easy. Okay, convection on areas, I'll select this length areas. You can see I'm going to select all these 4 areas. I've selected, you can see the count is 4. I've selected all these 4 areas. You may think that these 2 areas comes in rose color, and so that you may think that only these 2 areas are selected. No, this is something I don't really like in Ansys APDL, because you can't really find which areas are selected. So here I have selected this longer area. You can clearly see. Once again, if I click here, okay, very good, I have selected all these 2 areas. Once again click here, that that rose color goes away, and once again click here, the rose color goes away, and these two becomes rose. And what we might think is that, oh, I have mistakenly select this shorter and this shorter smaller area. No, that's not the fact. Here you can see the count is 4. I have selected these longer areas, but the answers is somehow showing that this 2 is in rose color. No, I have correspondingly selected. So you can just rotate your model using this dynamic model mode. If you select your right mouse button and you click, and if you rotate, it is rotate. If you click your red mouse left mouse button and if you move, it is just move. So I'll click, and you can see only these 4 areas are selected, not these 2 areas, right? But Ansys shows it mistakenly, so don't worry about that, right? So don't get confused by the way that I have selected wrongly. No, just for your reference, I'll say once again, go for convection areas. Just go to this middle area and start clicking one by one, and by the end you would have selected only these 4 longer areas and not these 2 short areas. This is a thumb up rule, keep that in mind, and click on OK. Now let me go to film coefficient, which is nothing but my convective heat transfer coefficient. Convective heat transfer coefficient is 22. So I can share here 22 watt per meter square degree Celsius. So this is my film coefficient, which is asking in Ansys. And the one thing is atmospheric temperature 35 degrees Celsius. So which I'm going to give it as film coefficient is nothing but my convective heat transfer coefficient, which is 22 watt per meter square Kelvin. So but the unit system that I'm using is mm. So I have to change this to mm, which is 22 E minus 6 watt per mm squared degree Celsius or Kelvin whatsoever, right? And bulk temperature, it's 35 degrees Celsius. As I have given the base temperature as 200 degrees Celsius, I have to give the bulk temperature in degrees Celsius, right? Don't worry about this load key, usually phase number, and don't just leave these constant values. Just give this film coefficient, and this bulk temperature refers the atmospheric temperature. So heat transfer coefficient and atmospheric temperature, these are the 2 things that you have to give input here, right? And then click on OK. So that's all. The boundary condition is over. So I have applied the base temperature, I have applied the convective heat transfer coefficient, and the other end is insulated, which means there is no convection. So that's all. My first boundary condition is over. The only thing that I have to do is solve the problem. So solution, solve current LS, and click on OK. So the element matrices are forming. Okay, it's taking a little bit of time because the number of elements is a little bit higher, hence it's taking some time to solve. So now the element results are being calculated, which means the assembly matrix is being done, and it's assembled, and it's being solved using the solver, which is present inside the Ansys APDL, which they have written using codes. Okay, so in a moment our solution will be done, and here we are. Yes, so the solution is done, right? Okay, now the thing remaining is we have to see the results. So one by one we'll start. So this is the problem that I have solved, short fin end insulated. So first thing, let us see the temperature distribution plot, and let us find the minimum temperature at the other end, right? And okay, so go to nodal plot results, contour plot, nodal solution, get on to DF solution, nodal temperature, and okay. So you can see the colorful, beautiful plot. So this is 200 degrees Celsius, and as it goes, the temperature gets on reduced, and the other end it's 83.1462. It's approximately 83.15. So it's nothing but 1462. You can round it off to 83.15. Nothing wrong in that, right? Okay. So which is closer to the analytical result of 83.19, right? Okay. So save this image. So I can always do that by plot control, write meta file, invert white or black, and you can save this result, right? So the first thing is completed. So we have found out the temperature distribution and you have found out the minimum temperature. Next you have to see the heat flux. Heat flux is nothing but Q by A. The formula is Q by A. Heat transfer rate divided by area is nothing but heat flux. So again, nodal solution, go to thermal flux, which is nothing but heat flux. Click on thermal flux vector sum and click on OK. So you think that nothing has changed. The values has changed here, so don't worry about the color. The color remains the same. The value has changed here. So it goes to 0.104203. So 0.104. The actual analytical is 0.097. It's approximately 0.1, and here also you have got 0.1. So it's closer match. So nothing to worry about. And also save this image. Go to plot control, write a meta file, and save this image. And so the second thing, which is heat flux Q by A, is completed. Next you have to find the temperature at a distance of 40 mm from the base, right? So in order to do that, so I'll introduce to a new option which is called as path operations. Get on to path operation, define a path. So what this means is that, so whatever the path you select in your model, the results along the path will be shown in this path operation. So I'll just explain to you. So define path. Initially you have to define a path in which you want to see the results. I want to see my results along the length of this fin, right? So that's what I'm going to do. So define path by node. So I'm going to select this one corner node, and I'm going to select this one corner node. I'll click on OK, and you have to select two end nodes. In order to create a path, you need 2 points. So one point is this end node, and the other point is this end node. This end node. So these are the two end nodes that I have selected, and once you join these 2 points, you will get a line. So that line is our path, right? So select the minimum two nodes you have to select. So select one end node here and select the other end node here. So this, if you join these two end nodes, it is going to be one of the vertex, or so one of the edges of this fin, and I'm going to see my result along this path. So click on OK. So you have to define a name for your path. So I'm going to see the temperature. So let me give it as TMP, and the number of data sets. So as my length is 160 mm, I want to see my temperature distribution for every 1 mm. So I'll give the number of data sets to be 1 mm and number of division to be 160. So I'll give both these. I'll give both as 160, which means I'm going to take 160 points and I'm going to see the temperature distribution for 160 points, which means I'll get the temperature distribution for every 1 mm. If you want to see the temperature distribution for every 0.5 mm, then the number of data sets should be double the length of the fin, which is 320. So you can see the temperature distribution plot for every 0.5 mm. But as far as now, I'll see it as 1 mm. The only thing that I need is the temperature at a distance of 40 mm from the base. So if I see it in the multiples of 1 mm, then I can easily get to the 40 mm easily. So I'll just click on OK. So the path is created. Now go to map onto path, and I'm going to see the temperature. So DO solution temperature, and the username label, let me give it as temperature, as I'm going to see temperature, and click on OK. Now plot path items. You can see it on a graph, or you can see it in a you can just see it as a list. So initially I'll show you the list. So I'll click on list path items, I'll click on the temperature, and I'll click on OK. So you can see the temperature at the 0 degree Celsius, it is 200. As the length, S is nothing but the length. As the length keeps on increasing, the temperature keeps on increasing. So, and finally at the length of 160 mm, you have the temperature of 83.146. But what I am interested to see is the temperature at a length of 40 mm. So here it is. The temperature at a length of 40 mm is 140.99. So what we have here, temperature at a distance of 40 mm is 140.99. I'll change this. So, but the actual value is 141.11. 140.99 is very much closer to 141.11, right? So we have a close match here, right? You can save this list, and also you can see all this list in the form of a graph. In order to do that, go for plot path item on graph, click on temperature and OK. And this is the distance and this is the temperature. At 0, which is the base, you have 200. As the fin length increases, you can see the increase in temperature, and at 160 mm you have 83.146. So this is a temperature distribution in the form of a graph. Also save this image. Go for plot control, write meta file, and click on invert white or black and save this image, right? So this is how you can see the temperature at any length. So not only at 40 mm, you can see the temperature along the length of the fin in any mm, whatever the you want, you can see using this option called as path operations. So my third one gets completed. So these three are things that we can see in Ansys. So in order to calculate this fin effectiveness and efficiency, in the formula you have to substitute the heat flux that you obtain from Ansys in order to get this green color results of fin effectiveness and fin efficiency, right? And this black color represents the theoretical value, which I have used this value 0.097, which I have substituted in fin effectiveness and fin efficiency formula to get this black color values. And in order to get this green color values, I have used the Ansys heat flux value and I have substituted in fin effectiveness and efficiency. But in Ansys APDL, you can't directly see the fin effectiveness and fin efficiency. That's not possible. So fin effectiveness and fin efficiency for the Ansys values, it should be calculated by substituting the heat flux of the Ansys value in the effectiveness and efficiency formula. I think I am making myself clear here, right? So this is how we have to compare all these results. So the first one is first problem is completed, first boundary condition fin is completed. The second one is short fin with end convection. So I don't need to redo the entire problem again. The only thing is that the second boundary condition, which is here, the second problem is that, so this is similar to the one with insulated, but the thing is that in end insulated you are not going to apply a convection here, but in with the end convection, this boundary condition, you are going to apply the convection also at this other end. So that's what I'm going to do. So in order to so instead of solving this entire problem again, what I can do is that I can apply the convection at this other end and I can just solve my problem very easily, right? So I'll just change this to plot volumes, right? And I'll go to preprocessor, loads, define loads, apply. I'll go to convection on areas and I'll select this small area and I'll click on OK and apply the same convection, which is 22E minus 6 watt per mm squared Kelvin and bulk temperature of 35 degrees Celsius at that location. I'll click on OK. Now I'll solve my problem. That's all. This is the second boundary condition that is being applied, and that's all. You don't need to redo the entire problem again to get this result. You can just apply the boundary condition and you can just solve, so that you'll get the results. So it's taking a time to solve. Yeah, the solution is completed. Now I'll go on to general post processor, plot results, nodal solution, and viewer solution, nodal temperature. Let me click on OK. So here the least minimum temperature is 81.5578. So save this image and let me compare it with this here. So 81.55. The actual answer is 78. I can add two more digits. So 81.5578. And the theoretical answer is 81.6, which very much closer to the Ansys value. And the heat flux, so save this image, then go to thermal flux, click on OK, and the value is 0.104502, and here it is 0.096, which is approximately closer to 0.1, and the Ansys value also 0.1, so it's OK. And similarly, for seeing the temperature at a distance of 40 mm, you can do the same path operation. So go for path operations, and I think the plot path is already there. So path status, define paths. Okay, the path has been erased, so I have to do that once more. So define path, go by nodes, click on this. Sorry, I'll click on this end node. I'll click on apply. Sorry, I have to select two nodes. So one is this end node, and this one is other end node. And now I'll click on OK. So the same temperature 160. So the path is created now. Now go to map onto path. So what I am going to see is the temperature, and the same temp is given here. Okay. Now plot path items and list path items. Okay. So temperature at a distance of 40 mm, it's 140.72, which is here 140.72, which is closer to 140.87 got from theoretical calculations. Good, right? And again you can save this list file, and also you can see the graph. Okay. and also save this graph using plot, write meta file, and invert white or black. So we're going to save 3 images. One is the temperature plot, another one is heat flux plot or the thermal flux plot, and the third one is on graph. And also you have to save this list, all these values for every 1 mm, save the values. So these are the 4 things that you are going to save. And one more, save the session editor of this file, so which I have already told in my earlier videos. So the best way to save an Ansys file is always saving this session editor file by copying all the data in this file by Ctrl A and Ctrl C. You can copy the data and paste it in a notepad file, and you can save it. And whenever you want to run it in any version of Ansys, just copy that and put it in here, or open the session editor again and paste it there. And if you click on OK, then the entire problem will be resolved again, right? So this is my second boundary condition. And the fin effectiveness and fin efficiency, as I already told you, you can use the heat flux got from the Ansys to get the fin effectiveness and fin efficiency for this Ansys. So it's closer, almost closer, right? Okay. Now let me get into the third condition, which is both ends are at the base temperature. So the convection is only going to happen along the longer phases, and the both ends the heat is going to be generated at 200 degrees Celsius. The base temperature is going to be 200 degrees Celsius. So this is my third problem. So in order to solve this problem, so my third problem is here. I'll show it to you here. Right. This is my third problem. So I will change this to fin, right? Okay, in the third problem, both the ends are at 200 degrees Celsius, and the heat is going to be conducted along the length, and along somewhere in the middle, the temperature is going to be the minimum value, right? Okay, so this is my problem. And so in order to solve the problem again completely, what I'll do is that I'll just delete the convection that I've applied earlier, and I'll apply the convection at that location. So this will save me some time. Instead of solving the entire problem, I can just delete the convection that I've applied for the earlier problem at this point, and I'll apply the temperature there, right? But if you want, you can solve the entire problem from once again, so that you would be easily recognizing the options, and you would be making yourself familiar with the Ansys, right? So for the time being, I'm just deleting this convection which I've applied for the area problem, thermal convection. So you don't need to do this way. You can solve the entire problem again and again for all the 3 boundary conditions, so in such a way that you'll get very much familiarized with the Ansys work menu for solving a fin problem, right? Which will be helpful for you in the examinations. So convection on areas, I'll select this area and I'll click on OK, and I'll select click on OK, right? Okay, so this convection that I have applied there has been deleted. So now I'll apply the temperature. Apply temperature on areas. I'll select, because both the ends are going to be at the base temperature, I have to apply 200 degrees Celsius, which I have already done. And now I have to apply the 200 degrees Celsius at this 200 degrees Celsius at that smaller area, so which is 200. I'll click on OK. So I have applied now. So now the problem gets converted into a short fin with both the ends at fixed base temperature. I'll solve the problem once again. Okay, now the solution is done. Let me see the results. First thing is that temperature distribution, plot results, nodal solution, derivative solution. No, this thermal gradient, I'll tell you what this is in the next upcoming composite wall tutorial. As far as now, we'll see only the temperature distribution and thermal flux, right? I'll select on OK. Here you can find that the temperature is being conducted from both the ways, and you have the minimum temperature at the middle. Whereas in earlier 2 cases, you'll have the minimum temperature at this one end location, because the base temperature is here, the minimum temperature will be here. Whereas in this case, as the both the ends are at the base temperature, you'll have the minimum temperature at the center, which is 145.788, and my theoretical answer is 145.94, which is very much closer to the Ansys values, right? Okay, now let me see the thermal flux. Go to here, and okay, so you can find some similarity with the short end with one end insulated, because this is nothing but a symmetrical model. If you cut at the exact center half, it would become a short fin with end insulated. So it's nothing but a mirror model of short fin with end insulated, right? Okay, but it's not actually. It's I'm just trying to get an analogous, but actually it is not the case, right? Okay, and here you can find the value as 0.082222, right? And here you have 0.08222, right? While you so here there is one small thing that you have to keep in mind, because the heat flux that you calculate from the theoretical calculation, that means that is here, yeah, fixed end temperature, the theoretical heat transfer rate that you calculate using this formula, and if you have to divide this by area, which is 12 cross 12 mm in this case. So once you divide this Q divided by the area, and what you will get is that you will get 0.16, okay, but actually here the length, what you should substitute it, that usually you will substitute it as 160 mm, because the length of the fin is 160 mm in this case. But what Ansys does is that Ansys takes this to be a symmetry. Ansys considers this that this is the maximum temperature and this is the minimum temperature, which occurs only at the 80 mm. So for calculating the heat flux, Ansys takes only this length and not the entire length of the fin. But actually you have to take the entire length of the fin, but Ansys, what it does is that it takes only the half the length, because you get only the minimum temperature here and the maximum temperature at this location, and hence the Ansys value would be 0.0822. But when if you substitute, if you calculate using this theoretical calculation formula here, if you substitute the length as 0.16, which is 160 mm, if you substitute 160 mm in this formula, and if you substitute all the other parameters, and if you divide this Q by area, what you will actually get is that here you will get it as 0.1594. So that's the value you will get, but you can't compare that 0.1594 with the Ansys, because Ansys only shows half of that value, approximately half of that value here, 0.0822, right? So in order to compare this heat flux with the Ansys value, substitute the length as 80 mm in this formula. Actually this is not the right thing to do, but in order to compare it with the Ansys, consider this problem to be symmetrical, and hence the length is going to be only 80 mm. So if you substitute 80 mm and calculate this Q value and divide it with the area, you'll get the heat flux as 0.09, which you can compare with Ansys, which is 0.08, very much closer, right? Okay, this is only one small hiccup here, but Ansys works differently than analytical in this case, right? So this is the only one way which you can compare your Ansys results with your analytical answer, right? Okay, then the final thing that you have to do is that calculate the temperature at distance of 40 mm. So in order to do that, you can create the path as similar. So save this image once again, go to path operations, define path by nodes, click this end node and click this end node, click this end node, and be careful while selecting the node, don't select this node instead, right? If you select, the path is going to be a diagonal one, and which will not get an actual value. The path should be the edge of this, should be any one of the edge of this square prism. So I'll select this edge, this one and this one, which is easier for me to select. Instead, if you select any other node in between, then the path is going to connect all those nodes, and the path is going to be a non-linear irregular one. You need a straight path which connects the end nodes of this square prism. So only then you will get a straight path. If you select any node in between like this, then you are going to get a path which is very much irregular, and the result that you get from out of this path is not going to be an accurate one. So select this node and this node. Be careful while selecting all these two corner nodes, okay, and click on OK. Now temperature 160, everything is similar, okay, and now let me map onto the path. Go to map onto, okay, and everything is same here, okay. Now plot path items on list path items, and okay. So here you can see the temperature goes on decreasing, and at 40 mm you get a value of 158.54, right? you get here 158.54, which is very much comparable with the analytical calculation of 158.72. Similarly, you can calculate the fin efficiency and effectiveness as I told before, right? So these are the things that you are going to do for your problem. Your problem is going to be any one of these boundary conditions. So you have to identify your problem, which boundary condition that I have to solve, use, and then solve the problem, then calculate all these 5 parameters and compare it with the Ansys results, right? So this is what you are going to do. Now if I plot this same results in a graph, okay, so you are going to see a U shape. That's because both the ends are at base temperature, and as the length goes on, as the length increases, the temperature decreases, and here as the length decreases, the temperature decreases, and exactly at the midpoint, because both the base temperature are at same 200 degrees Celsius, the minimum temperature is exactly at the midpoint. But this need not be the case always. The end temperature can be different here. See in this problem, this 200, here it may be 300 or 400 or any other value. So these two base temperature, it need not always be the same, it can be different. If it is different, then the minimum temperature will not be exactly at the center half. It will be somewhere shifted back and forth, and it will not be at the center. Here, as the base temperatures are same, the minimum temperature is exactly at 80 mm out of this 160 mm, right? So also save this image. So this is all about solving fin with the 3 boundary conditions. So long fin, which is not practically possible. Hence, we are solving the fin problem with any one of this 3 boundary condition. So I think I have made everything clear to you in this problem, right? So you are going to calculate all these 5 parameters. You are going to save the image of the temperature distribution, heat flux, and temperature, the path operation. You are going to save the graph and also the list results. So you are going to save 4 images, right? And so that's all. Okay, so I have completed my video tutorial. So if there is any doubt, any clarification, you can always contact me, right? So thank you all. That's all. We'll see you once again in the next upcoming tutorial on composite wall, sphere and cylinder, and we'll see how to solve it. So until then, see you. Bye.